Alright, so this video is going to deal with Newton's third law and action-reaction pairs. The first thing we're going to do is we're going to draw a free body diagram. As you notice, we've presented with a situation of a book sitting at rest on a table. So we're going to identify the forces that are acting on that book. I didn't make a box just because it's a little difficult for me in Word here. I just represented the book as a dot. So I'm going to take a force arrow and I'm going to place it pointing straight down, and this will represent the force of gravity. Now, if that were the only force, as we discussed in class, if that were the only force acting on the book, that thing would accelerate downwards. Since it's sitting at rest, and at rest are your key terms here. At rest means that forces are balanced, that the net force is zero. So that means there's got to be some other force that is identical, but in the opposite direction. So if this is the force of gravity pulling the book down, nice thing about doing this digitally is I can copy and I can paste that arrow. So now I have another arrow that's identical. However, it's going the wrong direction. So what I'm going to do is I'm going to take the top of this arrow and I'm going to pull it around this way. And I'm going to make sure that they're about the same length, which they are. And I'm going to put that arrow right on top here. You should be thinking, what is this upward force that's acting on the book? If it's at rest on the book, or on the table, it is the force of the table pushing back up. That has a specific name that we've talked about. That's called the normal force. N-O-R-M-A-L, the normal force. If I were a diligent student, I would put F with a subscript of an N right here for the normal force, and an F with a subscript of G. So gravity's pulling this thing down, the table's pushing it back up. It's an equal battle, so the book stays at rest. That's just sort of a review of what we've done before. Now writing the action-reaction pairs. For every interaction, anytime two objects interact with each other, we have what we're calling an action-reaction pair. For every action, there is an equal and opposite reaction. So the action here would be that gravity pulls the book down. If this is the action, to write the reaction, all that we really have to do is we just have to turn it around and rephrase it backwards. So instead of gravity pulling the book down, the book pulls gravity up. Does that make any sense? No. So is gravity? What is gravity? It's what's pulling the book down. And what we'll find out is that that's actually the earth is pulling the book down. And that means that the book pulls the earth up. And so there we have our action-reaction pair. And it's as simple as that. It can be a little bit more specific if we said the earth pulls the book down with a force of, the book weighs about a pound, so I'd say that's about 4.4 newtons. And so if the earth is pulling the book down with a force of 4.4 newtons, the book is pulling the earth up with a force of 4.4 newtons. You might start to think about Newton's second law and say, okay, so if this same force is applied on the book and on the earth, which one's going to accelerate more? If we could get rid of the table, right, if we didn't have this balancing force, if the earth pulled on the book with a force of 4.4 newtons, the book will accelerate. It'll take off. Now, if the book pulls back on the earth with a force of 4, if we pull on the earth with a force of 4 newtons, 1 pound of force pulling on the earth, that's not going to move the earth. It's not going to accelerate the earth. The earth's going to basically stay still. And so that's why we have the situation where one thing will accelerate while the other thing doesn't really accelerate. Looking at problem 2, I'll get you started here. I'll help you with the free body diagram, and then I'll do the action. I'll let you go to the reaction. So if you're totally confident with this, go ahead and practice it. Go ahead and try and answer this, and then come back and check and see if you got it right. Hit pause or something. So a girl is pushing a book across the table. So the forces that are acting, again, we have gravity acting down. I'm going to go ahead and throw, say it's the same book, so it's got the same weight, so I can just copy and paste these arrows. The table is pushing back up. So it's going to have the same normal force. It's not accelerating up, it's not accelerating down. It's at rest on the table. But now a girl is pushing it across the table. So what's the free body diagram look like there? We'll assume that she's pushing it with constant velocity. So what I'm going to do is I'm going to insert another arrow, but this arrow is going to represent the girl pushing the book across the table. So here she is pushing, and we'll say she's pushing with a big force. And then we're going to put a resistive force because it's sliding on the table, so there is a little bit of resistance there, a little bit of friction, and so this arrow will represent the force of friction that resists that motion. And so if we have this scenario for the free body diagram, our vertical forces, gravity and the normal force, are balanced. Our horizontal forces, the force of the girl pulling on it and friction, are not balanced. So we have what's called a net force here. So this thing is going to accelerate to the right. Reaction pair, action, reaction pair. So what's the action here? It's a girl. So girl pushes book right. The reaction, I'll give you a hint. It's something pushes something to the left. And if you're thinking about it, it's probably not a push, but it's more of a pull. She pulls it, or she pushes, it pulls. So see if you can fill it in. Look at what we did here. We reversed the sentence. Earth pulls book down, book pulls earth up. Girl pushes book right. Something pulls something to the left. Hopefully that helps. You can go ahead and answer the rest of the questions. And that's all, folks.